Welcome to One Chemistry. As a part of our understanding, we are seeing organic chemistry concepts. In this video, we are going to see Michael addition. We will learn deeply with 24 solved examples. Stay tuned. What is inside this video? First, we will see what is Michael addition, the difference between 1,2 addition and 1,4 addition, then comparing the nucleophile hard versus soft, then the advanced concept Michael donor and acceptor. Further, we will see 24 solved examples, those examples from various examinations. First, let us see what is Michael addition and basics of it. Initially, we keep the things simple. Here alpha, beta and saturated ketone is there. Nucleophile is adding. Nucleophile can add in ketone or alkene, that is second position and fourth position, which is called 1,2 addition and 1,4 addition. When it will happen? If it is a hard nucleophile, 1,2 addition happen. If it is a soft nucleophile, 1,4 addition happen. You should memorize this fact. Hard mean 1,2, soft mean 1,4. If you have confusion, take F from soft, expand it as 4. So soft mean 1,4 addition. First, let us see 1,2 addition in very detailed way. 1,2 addition mean hard nucleophile attack the second carbonyl. It attacks, you have the double bond mobility and O minus is there. Finally, it conjures OH. So if you look at it, second position methyl added, first position alcohol added. That's why it is called 1,2 addition. Then the 1,4 addition, which is called Michael addition. Here the nucleophile added to the fourth carbon. Fourth carbon, the charge mobilizes, the electron delocalizes. You have O minus there. Then it converts into alcohol. Then you have enol situation. Enol converted into ketone. It's a tautomerism. If you look at finally, methyl added at 4, hydrogen added at first carbon. That is why it is called 1,4 addition. So 1,2 addition and 1,4 addition, the naming you should know. You may wonder why 1,2 and why 1,4 addition. Here carbonyl is the hard electrophile, meaning the charge is localized on small atom, so it's considered as hard. So hard soft principle, hard interact mean carbonyl is a hard electrophile, interacts with hard nucleophile. That is why you have 1,4 addition. Soft is opposite, you have 1,4 addition. So you should know the fact that hard soft interaction decides the regioselectivity of 1,2 and 1,4 addition. Then the important question you might ask, which is soft nucleophile, which is hard nucleophile. Basically you memorize it because it will help you to solve many problems quick and easy way. Soft nucleophiles are mostly bulky with copper, and carbon nucleophile, which is enolates, mostly it is soft nucleophile. Then cyanide, amine, thiol, alcohol and halides, then enamines, then importantly sulfoxide halide. Then the hard nucleophile, opposite to soft nucleophile, high in charge, small in size, which is methyl magnesium bromide, basically Grignard reagents, fluorine and butyl lithium, methyl lithium, all alkyl lithiums, and sulfur halide. Sulfoxy halide is soft, sulfur halide is hard, and alkene and aromatic system. So basically you should know what is hard nucleophile, what is soft nucleophile. Then you should know the advanced concept, Michael donor and acceptor. This will come with organic nucleophile, basically carbon nucleophile. You can imagine straight away all carbon nucleophiles are soft. Mostly it will come with 2 electron withdrawing group. Basically it's a Michael donor. The electron withdrawing group can be cyanide or carbonyl. Carbonyl with ketone or ester, or it can be nitro group. So apart from common nucleophile, you should know Michael donor. So what are all Michael acceptor? This is easy. Alkene with electron withdrawing group. Most of the time you will see carbonyl, aldehyde or ketone. Sometime it is with cyanide or ester or diester. So you should know the difference between Michael donor and Michael acceptor and common examples. Then we will solve our problem to improve our understanding. Why so many problem in problem gives better perspective, better way to understand the concept. So we will solve as many as possible. Let us see first example. Here we have alpha, beta unsaturated ketone. You are reacting with thiol. You should find what will be the final product. This is the typical Michael addition example. Sulfur is the soft nucleophile because sulfur is big, polarizable and soft. If the nucleophile is soft mean you have 1,4 addition or Michael addition. Hard mean 1,2 addition. Here 1,4 addition is the possibility. So thiol add at the fourth position. Double bond delocalizes. You have one nucleophile. Then H plus added. You have alcohol. If you look at closely, alcohol is enol. It convert into ketone. So methyl added the fourth position. Hydrogen added the first position. So 1,4 addition happened. Thiol added to the fourth position. The concept you got learned here is soft nucleophile will add in the 1,4 position. Then the next example, you have cyclohexane alkene which is alpha beta unsaturated ketone. You are reacting with hydrogen cyanide and potassium cyanide. You should find what will be the final product. If you know the fact that cyanide is the soft nucleophile mean you know it is a 1,4 addition which is Michael addition. The Michael addition product is major, 1,2 addition is minor here. If you look at the mechanism, cyanide added to the fourth carbon, double bond delocalizes and you have O minus which is quenched as OH. There hetoenol tautomerism possible. Alcohol become ketone, you have the final product. So the major product is 1,4 addition product. The concept we outline here is cyanide is the soft nucleophile. Then the next example, you have cyclohexanone, alpha position you have alkyl group and you have alpha beta unsaturated compound with butyl lithium. You should find what will be the final product. Here you have ketone, there is a enolate formation, but in enolate, more substituted enolate will form. So enolate formed at the alkyl side. Enolate become nucleophile there. Enolate is the soft nucleophile, so which will undergo 1,4 addition. Since the reaction has continuous possibility, further enolate forms, it has aldol condensation and alkene elimination. Here our interest is Michael addition. So enolate, more substituted enolate will form. Enolates are soft nucleophile. Then the next example. Here you have alpha beta unsaturated cyclohexanone and you have methyl group at the fourth position. You are reacting with halide chloride with copper and magnesium organometallic compound. You should find what will be the final product. Here you have copper. Copper always promote the soft nucleophile. So copper based nucleophiles are soft. It will undergo 1,4 addition. So methyl group add to the fourth position which is the major one. Then you have nucleophile. Because you don't have any quenching pathway, the nucleophile is carbon nucleophile which attacks the chloride. You have new CC bond. So the concept you have to learn here is Michael addition can also generate a new nucleophile which in turn acts like normal one. Then the next example, you have cyclohexene attached with amine. It is like enamine. You are reacting with alpha, beta and saturated ketone and you are using acid hydrolysis. You should find what will be the final product. Here you have enamine. Enamine can act as a nucleophile by donation of lone pair, so carbon nucleophile form, which is the soft nucleophile. Since soft nucleophile undergo 1,4 Michael addition, which attacks the fourth position of the alkene. So 1,4 addition happened. You have carbon-carbon bond formation. Further, you have hydrolysis, mean it remove the amine. You have ketone there. So the concept you outline here is enamines will create soft nucleophile which will undergo 1,4 addition. Then the next example, you have cyclohexenone reacting with lithium copper organometallic compound with cyanide and trimethylsilyl chloride. You should find what will be the final product. Since it is a conjugated ketone, you have the possibility of Michael addition. Since copper provides soft nucleophile, 1,4 Michael addition is possible. So nucleophile adds, you have fourth position, carbon-carbon bond. Double bond migrates, you have O nucleophile. O nucleophile further attacks halide, you have O silicon bond. Here it is not enol, so the reaction stops here. The concept you outline here is whenever you see copper nucleophile, blindly you do 1,4 Michael addition reaction. Then the next example, you have cyclohexenone reacting with sulfoxide halide which has CH2 nucleophile. You should find what will be the final product. Here you have sulfoxyhalide. Sulfoxylates are bulky and soft, so it acts like a Michael donut. So 1,4 addition is possible since starting middle is conjugated ketone. Fourth position it adds, you have charge travel there. The delocalization, again it creates the internal nucleophile which is the new one which attacks dimethyl sulfoxide eliminates. You have cyclopropane ring. So the new ring formation from the halide. The concept you outline here is sulfoxide nucleophiles are soft which will undergo 1,4 Michael addition. Then the next example, you have cyclohexenone. In third position, you have O-methyl group reacting with phenyl magnesium bromide in acidic condition. We should find what will be the final product. Here you have phenyl magnesium bromide. Magnesium is hard, provide the hard nucleophile, so which will undergo 1,4 addition. So phenyl add to the second position, you have alcohol. The condition is acidic, so alcohol become H2O and eliminated. The mesomeric effect on the oxygen help for the delocalization and removal of H2O. Finally, you have conjugated ketone at the O-methyl group. Then the methyl group eliminates, you have conjugated ketone. Why this is important? Because starting middle is 1,2 addition, but final product look like 1,4 addition. All this possible because of acidic condition. That is the magic of chemistry here. So the concept you outline here is, so you should master the reaction condition to master the Michael addition. Then the next example, you have cyclohexenone. 1,4 position you have alkyl and isopropenyl. You are reacting with sulfur halide which is CH2 minus, and you should find what will be the final product. Here you have sulfur halide. Sulfur halides are hard because of localized charges, so it will undergo 1,2 addition. Carbon attacks. Then you have O nucleophile. Since you have dimethyl sulfur as the leaving group, O minus attacks CH2. You have cyclopropane formation. This reaction involves regioselectivity. The regioselectivity promoted by the nucleophilicity. Since sulfur halides are soft, only 1-2 pi bonds get methylated, not the conjugated alkene or isolated alkene. The concept you outline here is the sulfur nucleophiles are hard, it will undergo 1,2 addition. Then the next example, which is similar to previous one. Here you have cyclohexenone with methyl and isopropanol with sulfoxide halide, CH2 as the nucleophile. You should find what will be the final product. Here you have sulfoxyhalide. Sulfoxyhalides are soft. It will undergo 1,4 addition. So it will add to the fourth position. New CC bond forms. Further, you have one nucleophile. The charge travels. Since dimethyl sulfoxide is a good leaving group, new methylene bond forms. Cyclopropane ring finally created. If you look at it, regioselectivity by nucleophilicity, because soft nucleophile promote the 1,4 addition. So pi bonds of carbonyl is not attacked. Isolated alkene is not attacked. Only conjugated alkene is attacked here. So the nucleophile creates the regioselectivity. Then the next example. Here you have linear compound with dicarbonyl. One is ketone, another is ester. Reacting with sodium methoxide and alpha beta unsaturated ketone. You should find what will be the final product. Here you have Michael donor because you are having active hydrogen between two electron withdrawing carbonyl. So you generate the nucleophile. Basically it's a Michael donor there. It will undergo 1,4 addition. So the nucleophile adds to the fourth carbon. You have bond migration, double bond delocalizes. You have enol there. Then the enol convert into ketone. You have the final product. The concept you have to learn here is active methylene groups are Michael donor. It will undergo 1,4 addition. Then the next example, you have diester which is connected through terminal double bond and you are reacting with methylamine. You should find what will be the final product. Here you have diester, it may confusing. If you look at it, it's a Michael acceptor because it is alkene with two electron withdrawing group. Amine is the soft nucleophile. So soft nucleophile undergo 1,4 addition. So fourth position it attacks, you have 1,4 addition. The double bond migrates, you have enol there. Enol converted into ketone by ketoenol tautomerism. So the concept you have to learn here is whenever you look at the alkene with electron withdrawing carbonyl system, you might realize the Michael acceptor, it will undergo 1,4 addition. Then the next example, you have vinyl cyanide with methylamine. You should find what will be the final product. If you look at the plain side, you might confuse how cyanide become Michael acceptor. If you redraw properly cyanide, you might realize alkene with electron withdrawing group and conjugation. So it is the Michael acceptor. Amine is the soft nucleophile. So it can undergo 1,4 addition here. So amine added to the fourth position, double bond migrate. You have nucleophile. You have negative charge at nitrogen. Finally, it rearrange. You have final 1,4 addition product. The concept you have to learn here is amine is the soft nucleophile. Vinyl cyanide is the Michael acceptor. Then the next example, you have cyclohexadiene with dienone. Basically, it's a quinone form. In second position, you are having methyl group. You are reacting with ethylamine. You should find what will be the final product. Here you have amine. Amine is the soft nucleophile. It can attack many positions. There are 4 Michael positions possible. Only one is the major product because it creates more substituted alkene. Other position leads to the less substituted alkene. So more substituted alkene is the final product. Then alkene rearranges. Then ketone rearranges to form enol. Finally, you have aromatic compound. So aromaticity drives the reaction. The concept you have to learn here is whenever you have the possibility of nucleophile formation, more substituted alkene will form. Then the next example, you have alpha beta unsaturated ester, which is O-methyl ester. You are reacting with imidazole. You should find what will be the final product. Here you have Michael acceptor, Michael donor. Michael donor has two possibilities, sp2 hybridized nitrogen, sp hybridized nitrogen. Here if you look at it, nitrogen with sp2 hybridization reacts because of nucleophilicity. If you look at the hybridization, sp2 hybridization has the high electronegativity. So what really happens is, it won't donate the electron, it will become poor nucleophile. So sp3 carbon is the better nucleophile which attacks. You have the final product which is sp3 hybridized nitrogen. The concept you have to learn here is, in nucleophilicity, the electron donation is important. sp3 nitrogen is less electronegative which attacks. You have final Michael product. Then the next example, you have benzene with side chain alkene and nitro group and you are reacting with cyclohexanone. You should find what will be the final product. Here nitro group is the Michael donor. You should imagine the reaction. So if you redraw, the reaction will be easy. So the addition happen at the Michael position, which is a fourth position. Michael donor act as the nucleophile, attacks the fourth carbon. You have Michael addition product. The concept you have to learn here is, in vinyl nitro situation, the first carbon will act as the Michael acceptor. Then the next example, you have cycloheptadienon. You are reacting with siloxyl nucleophile which is attached with O-butyl. Titanium tetrachloride you are using. You should find what will be the final product. Here if you look at it, silyl always stabilize the enol form. So it form enolate easily. So it is the carbon nucleophile, Michael donor. It attacks the fourth position. You have new CC bond. You have enol situation. Enol become ketone. You have the final product. The concept you have to learn here is, whenever you look at trimethylsilide, you might imagine enolate presence and use it as the Michael donor. Then the next example, you have diketone and methyl which is in the cyclohexane. You are reacting with alpha, beta and saturated ketone. Butyl lithium you are using. You should find what will be the final product. Here we are generating the carbon nucleophile which is the soft nucleophile. Even though it has many possibilities, more substituted enolate will form which attacks the fourth position. You have the Michael addition. The Michael addition leads to the carbon-carbon bond formation which can undergo further aldol reaction. Ring closure happen. Finally, you have conjugated ketone. Our interest is Michael addition here. First step is interesting because of the enolate. The concept you have to learn here is, even though the compound has many hydrogen, more substituted enolate will form. Then we will see different examples with different Michael donor and acceptor. Basically, we are comparing the Michael donors. These examples will help you to compare and contrast. We will see one by one. The first comparison will be, you have conjugated ketone which is alpha, beta and saturation. You are reacting with alkyl lithium and thiol. You should find what will be the final product. Here you have same Michael acceptor but two different Michael donor, thiol and alkyl lithium, both having nucleophile as R minus. One having nucleophile R minus, other is RS minus. The sulfur nucleophiles are soft. It will undergo 1,4 addition. So addition happen at fourth carbon. Delocalization happen. You have enol there. Then the enol tautomerize, you have final ketone. On the contrary, if you use alkyl lithium, methyl group is the nucleophile which will undergo 1,2 addition. R minus add to the second carbon. O minus form it quenched with H plus. So alkyl nucleophiles provide R minus, which is hard nucleophile, undergo 1,2 addition. Thiol provide Rs minus, which is soft nucleophile, which will undergo 1,4 addition. Then the next example, you have alpha beta unsaturated cyclopentanone. Here you have two different Michael donor. One is with 5 member, another with 5 member and 6 member fused system. You should find what will be the final product. Even though the reaction is complicated, the answer is simple. Here, both reactions involve nitrogen as the nucleophile. Both are soft nucleophile, undergo 1,4 addition, but which nitrogen adds? Here, sp3 and sp2 carbon is there. sp2 carbon is more electronegative because of more s character. So, sp3 nitrogen will be better nucleophile. So sp3 nitrogen will use 1,4 addition happen. You have final Michael product at both cases. First case only sp3 nitrogen is there. Imidazole moiety attacks, you have new CN bond. Another case also only one sp3 nitrogen is there. It attacks, you have final product. So the concept you outline here is the hybridization of the nucleophile is important. Less electronegative nucleophile attacks, you have final product. Then the next example, you have cyclohexenone, alpha, beta unsaturated ketone. You are reacting with two different Michael donor. One is methyl magnesium bromide, another is dimethyl copper lithium. You should find what will be the final product. Here two different Michael donor, methyl magnesium bromide and copper lithium. Magnesium provides hard nucleophile. Hard nucleophile undergo 1,2 addition because carbonyl is hard interaction leads to the 1,2 addition. On the contrary, if you use copper nucleophile, copper is the big one, polarizable, which will undergo 1,4 addition, which is Michael addition. So CH3 minus add to the fourth position. You have enol with delocalization. Further, hetoenol tautomerism occur. You have the final product. The concept you have to learn here is magnesium nucleophiles are hard, copper nucleophiles are soft. That's why copper nucleophile undergo 1,4 addition. Then the next example, you have cyclohexenone reacting with sulfur halide, which is CH2 minus, and sulfoxide halide, which is also CH2 minus. You should find what will be the final product. Here you should know the fact that sulfur nucleophiles are hard, sulfoxide nucleophiles are soft. So sulfur halides attacks the 1,2 position. You have O minus, which is the internal nucleophile, and you have the possibility of leaving group dimethyl sulfide. So O minus attacks, you have epoxide formation. On the contrary, if you use sulfoxide, it is the soft nucleophile which will undergo 1,4 addition. Nucleophile attacks, charge travels. You have nucleophile which is internally formed, which attacks sulfur again. You have cyclopropane ring formation. So you have two different nucleophile, two different reaction. First is 1,2 addition, second is 1,4 addition. The concept you outline here is sulfur nucleophiles are hard, sulfoxide nucleophiles are soft. That's why sulfoxide halides undergo 1,4 Michael addition. Then the next example, you have cyclohexenone and you have methyl and isopropenyl in 1,4 position. You have sulfur halide with CH2 minus, sulfoxide halide with CH2 minus. You should find what will be the final product. Here you have similar situation, soft and hard situation. Sulfur nucleophiles are hard, it will undergo 1,2 addition. Sulfoxide ylides are soft, which will undergo 1,4 addition. So sulfoxide ylide add at the 4th position. You have internal nucleophile formation. The nucleophile attack again because you have the possibility of sulfoxide elimination. You have final methylation. On the contrary, sulfur nucleophiles are hard, which will undergo 1,2 addition. So it will add to the carbonyl, which will form internal nucleophile, which attacks the carbon. You have epoxide formation. First case cyclopropane formation. Second case epoxide formation. The concept you have to learn here is sulfur nucleophiles are hard nucleophiles. Sulfoxide ylides are soft nucleophile which will undergo 1,4 addition. On the contrary, sulfur ylides are hard which will undergo 1,2 addition. Then next and final example, you have cyclohexenone reacting with sodium borohydride and methanol and sodium borohydride and cetic chloride. You should find what will be the final product. Here you have same reagent but one catalyst is added which is cerium chloride. Cerium chloride promote the electrophilicity of the carbonyl. So what really happened? It will become reactive. The attack happened which is nucleophilic attack of H minus happen at 1,2 position. So 1,2 addition happen in terms of cetic chloride. On the contrary, if you use mere sodium borohydride which is providing H minus soft nucleophile which will undergo 1,4 addition. The enol forms, tautomerism happen. Finally, you have the ketone. So two different reagent, two different product. So one addition of reagent creates the different product. The concept you have to learn here is cerium activate the carbonyl which promote 1,2 addition. Finally, we see the summary. The nucleophilicity you should look at for the Michael addition. Hard nucleophile undergo 1,2 addition. Soft nucleophile undergo 1,4 addition. Soft nucleophile basically a copper nucleophile. Enolates, cyanide, thiol, amine, alcohol and halides, enamines and sulfoxide ylides. To generally memorize, soft nucleophiles are low charge and big size. On the contrary, hard nucleophiles are high charge, small size. Methyl magnesium bromide is common, then fluoride, then methyl lithium, sulfur ylides, alkene and aromatic compounds.